So hi everyone, thanks for joining the webinar, Lightweight Transaction with Scylla and Apache Cassandra. A little bit about Scylla, the company, before we dive into the product and the Lightweight Transaction. So we are ScyllaDB, the company behind the Scylla project. Scylla is a NoSQL database, a drop-in replacement for Apache Cassandra with superior performance and lower latency. And by drop-in in this context, I mean that it's compatible at the CQL level. Meaning that you have an application that works with Apache Cassandra, it will work as is with Scylla because it's used the same protocol, the same drivers. And with Lightweight Transaction, we're actually closing the last gap we had from Apache Cassandra from a functional perspective. So if you use the Apache Cassandra with Lightweight Transaction, you can now start using it with Scylla as well, and we'll explain how during this webinar. Scylla, you can use Scylla in 3 variants. The first is open source. You can download the code from GitHub and compile it if you like to do this kind of things. You can download the binary packages. You can use an AMI or you can use a Docker. We also have a Scylla Enterprise version, which is a closed source project based on the open source, but with a few extra features around cluster management and security. And last but not least, we have Scylla Cloud. Scylla Cloud is actually database as a service where we offer Scylla Enterprise, but you don't have to install it. You can just consume it as a service. Scylla is now close to 100 employees, and we are hiring. So if you know anyone, C++ developer in particular, Python, Golang, that are interested in databases, maybe they should contact us. Let me introduce myself and my co-host. So I'm Zach Leviatan, VP of Product at ScyllaDB, working for many years on software, and full disclosure, the picture is actually from a few years ago. So I don't look as good right now. Kostya, will let you introduce yourself.
Hi, I'm also not looking as good as on the picture. And I also spent a lot of time with databases, having fun. And at Scylla, I'm responsible for lightweight transaction support and implementation and further developments like synchronous replication and RAFT.
Okay, thanks, Kostya. So the way that we build this webinar is, first I'm going to give introduction to eventual consistency in Scylla, what we have in Scylla right now and what we have for the last few years. Then I'm gonna hand over to Kostya to deep dive into lightweight transaction, and especially how we improve lightweight transaction compared to what the Apache Cassandra have. And the last part will be roadmap and hopefully time for Q&A. As mentioned, you can write questions using the Zoom Q&A already, but we're only going to review them at the end of the session. So eventual consistency, I'm sure that all of you or most of you are familiar with the CAP theorem. You can raise your hand if you are not familiar. I can't really see you, but you can. So Scylla, Cassandra, DynamoDB are all fall into the same category of database, NoSQL distributed database that prefer availability on top of consistency. That means that basically the database will continue to work and will continue to accept writes, even if a few of the nodes are down, and we'll explain exactly how in a few minutes. So when you try to understand, when you start learning, I guess, Scylla consistency, 2 main terms you need to understand. The first is replication factor, and the second is consistency level. So replication factor is basically the number of replication or number of time you duplicate the information across the cluster, meaning on different physical nodes. So if you are using the most common replication factor of 3, the data will be replicated 3 times over 3 physical nodes. Of course, physical can be a virtual machine, but you can assume it's a persistent physical entity. You can specify a different replication factor per data cluster if you want to. For example, 3 replication in US1, 4 replication in US4, etc. And you can set the replication factor per key space. A key space, for those of you not familiar, it's like a collection of tables in Scylla. So you can have one key space with one replication and another key space with a different replication strategy, depending where the data is more relevant and where you want to replicate. Consistency level. So consistency level basically allow you to play or adjust the trade-off between consistency and availability. This is why we sometimes call databases like Apache, Cassandra, and Scylla to have tunable consistency. The consistency is actually applied per request. It's not a definition per key space, it's per request. So for each request that you send to the database, it can be either a read request or a write request. You can specify what the consistency level you want to have, starting from consistency level of 1, meaning that it's enough that one of the replication act back to send a response to the user, a success response to the user. Consistency level all, which require all of the replication to answer. As you can understand, this kind of strategy minimizes availability, because if one of the replication is down, the client will get an error using consistency level of all. And consistency level of quorum, that if, for example, you're using a replication factor of 3, quorum will require you answer from 2 replicas. And I hope the next few diagrams will explain it a little bit better. So the first one is a consistency level of 1. The client sends the information to the coordinator. The coordinator is a random node in ScyllaDB that get the first message. The coordinator will send the write to 3 replicas, 3 nodes. If we're using consistency level of 1, the coordinator will only wait for one of the replica to respond before he send an ACK or success back to the client. Of course, as you probably understand, you are not sure what happened with the other replicas. You don't know if it was a success or failure. It's basically done offline and will be synchronized at some point in the future. This is why we call it eventual consistency. If we're using consistency level of quorum, then you basically require 2 of the replication to send the response back to the coordinator. And the same go for reads. Okay, so both reads and writes have all of this variant of consistency level, and you can use, for example, consistency level of 1 when you are writing, and consistency level of quorum when you are reading, or whatever combination that you want. And you can use all of them with different key spaces and different queries. And I'm not going into a multi-data center, but you can control that as well. So I mentioned that you can have a variant of consistency versus availability. So the rule of thumb is that if your read consistency plus write consistency is bigger than your replication factor, then you are in a strong consistency land, meaning that you will always read the last write. But if your read consistency and write consistency together are equal or smaller than the replication factor, you are working with eventual consistency. That means that you might, in some cases, read stalled data. And you are willing to accept this for a better performance. So I mentioned eventual consistency, and I mentioned that in some cases, the data might not be written to all the replicas, and the user actually get a success. So when and how this data is synchronized. So there are 3 mechanisms to do that with the Scylla, and all of this, by the way, is also true for Apache Cassandra. The first is hinted handoff, the second read repair, and the most important is repair. Repair is a recurrent offline process that you usually run weekly. And it's basically synchronize each 2 nodes or each 3 nodes with a replica with each other, regardless of what the difference was before. After a repair is successfully completed, you know for a fact that the data is synchronized between all the nodes. As I mentioned, it's very recommended to run this every week, and we actually have a specific tool called Scylla Manager that help you run weekly or monthly repair, depending on your grace period, and report the results. One thing I didn't mention so far is conditional update. Conditional update is a query that allows you to read information before you actually write it and test it. And for that, I'm going to hand over to Kostya to dive into lightweight transaction.
Thank you. So let's begin. Could you just jump to the next slide, sir? Thank you. Before I will go over lightweight transaction details, implementation performance, you can try it now. There is a Scylla 3.2 available as an AMI. The documentation for conditional updates is also online. Go use it, go play with it. Next slide, please. So what are lightweight transactions? In this example, you can see that Scylla actually always writes data. All statements that modify data always leave a footprint in it. There are two reasons for this. One is eventual consistency. So even in case, even if we read some old record, then the other node might be doing just the same in parallel. So the value that we read, we cannot trust. And the second reason is that log structured merge trees that are used to store data in Scylla are optimized for write. So reads are way more expensive in log structured merge trees. So we are better avoid them. And in this example, the update statement is actually doing an insert, which is not always what you want. Welcome lightweight transactions or conditional updates. Next slide, please. So a conditional statement is introduced just for the thing. It allows you to read the old value, check the old value before you perform the mutation, perform the operation. And this statement is more like in a traditional SQL database, will not do an update if the record is not there. Next slide, please. So what statements can be conditional? Every single mutational statement can be conditional. Insert, update, or delete. There are some handy shortcuts for checks whether a row does exist or does not exist. So you can insert something if it does exist, or if it doesn't exist, or delete something only if it does exist. In this case, you avoid the eventual consistency sort of artifact when you delete a record and it's resurrected because the timestamp of your deletion is actually older than the timestamp of a concurrent update. Next slide, please. You can also use conditional statements in a batch. So conditional statements and lightweight transactions are used interchangeably. All conditional statements are transactional, so they are all follow these properties of transactions like all or nothing, durability, and isolation from other statements, and so on. But with batches, if a batch contains at least one conditional statement and it can have many, then the entire batch is atomic. It's executed as all or nothing. In case a batch has a single statement, then before applying the batch, we check the conditions of this particular record that is used in this statement. If there are multiple conditional statements in the batch, all of the conditions in all of the statements have to be true for the batch to be applied. Next slide, please. So while we are looking at this, I would like to mention a small difference between Scylla and Cassandra. If you look at the result set returned by a conditional statement, it actually returns the old row. It's useful if the row is not found, so you know that the statement was not applied, and that this is why the first column in the result set is whether or not the statement was applied. And it's also useful if the statement was applied, you can see the old values. So you can actually fetch the old values as an artifact of doing an update. Next slide, please. So let's look at conditional statement execution. How does it work? You probably know that in Scylla, a client can supply a timestamp, and this timestamp is used for the mutation. This doesn't make a lot of sense for conditional statement execution because you want to make sure that all of the conditional statements form a strict order. So one statement is executed strictly after another. It's a difficult word for me tonight. So, and this is why the first step before a transaction is executed is that the coordinator that is working on behalf of the client to make this mutation, to apply this mutation, needs to assume leadership. So in Scylla, this kind of locking mechanism is done per key, per partition key. And essentially this ensures isolation on partition level. This is how we make sure that, for example, conditional batches that modify multiple rows in the partition, they are applied atomically. The next step is repair that needs to take place if the previous round for whatever reason was unsuccessful. And this is obviously optional. And next, conditional update searches for the old row and then checks the conditions. So you might ask whether if conditions and where clause are similar or different. So they're very similar in what you can use on them, but they are different in the way they are executed. So where clause is used for search, and where clause can utilize indexes, secondary keys, if you have them, and conditions are checked after the row is found. So when we retrieve the row, we check the condition. Next is we build a mutation, and when we construct the mutation, we already know the values of the previous rows on all of the replicas. So we can assign this mutation the highest timestamp. It's either the current timestamp on the coordinator, or if any of the mutation has a higher timestamp than that, then it's higher than that. So we always make sure that the timestamp that is assigned to the mutation is higher than any previous timestamp on that mutation. And this is why you cannot supply a client timestamp on conditional updates. And with the assigned timestamp, the mutation is sent to all of the peers, they store it, and by that, the coordinator knows that, hey, this is durable. Now we can proceed and commit the transaction, because the majority of replicas store the mutation. And this property is also called quorum intersection rule. So like by storing the mutation on a majority before committing a transaction, we ensure that even if any non-majority of replicas disappear for whatever reason, the network partitioning or node failure, we preserve the continuity of the history on this particular key. So every key has this history of mutations associated with it, and for every key, we preserve it. So this is how lightweight transactions work. And by discussing how they work, I also sort of presented some of the basic limitations or constraints that you need to be aware of when using them. Next slide, please. We, in 3.2, we not only implemented lightweight transaction support, we also added a few new metrics so that some of the states of the database can be easily monitored. And basically, if any of the metrics here, except like the most basic one, like CAS write count is high, you need to take action. So why is CAS, first of all? CAS is a historical name for lightweight transactions. So lightweight transactions come under many names. It's like conditional updates, lightweight transaction, CAS updates, CAS writes, or Paxos writes, wherever. So CAS means compare and swap. It comes from the computer science term for atomic change of a single register. So that's the basic idea behind lightweight transactions as well. So CAS write counts by instance is the number of transactions that are running on the instance. Timeouts is something bad. If you have timeouts, you know, this whole algorithm is like 4 steps that I mentioned in the previous slide. So there is a special timeout setting for lightweight transaction writes. So if you have timeouts and something is wrong, probably the load is too high, so some of the writes cannot make it in time and so on. So conditions not met. This looks like a pretty normal thing, but once again, if you think about it, why would you do so many updates if most of them do not come through? So you need to keep an eye on that as well. And cast write unfinished commit is also an example of something going wrong, either because of node failures or because of the contention, which you need to keep an eye on. Next slide, please.
One thing, Kosta, sorry for jumping in. One thing I want to mention, the dashboard that you're seeing here actually available from the Scylla monitoring stack. So if you're
Yeah, so this is a
installing,
standard Grafana dashboard. Thanks for mentioning it, that we provide. And the metrics that I've talked about, if you want to just go hardcore and query them from the command line, these are the names of the metrics that I've been describing so far. Next slide, please. So now let's talk a little bit about the performance. 3 months ago, we presented the first version of lightweight transactions, and we did a surrogate artificial, more or less, workload to test them. It still highlights the limits of lightweight transactions. So if you are interested in everything about lightweight transaction support in Scylla, I also recommend watching the Scylla Summit talk, sort of a previous version of this webinar. Here we have a lot of important updates. So today we switched actually to a more standardized benchmark to measure lightweight transactions performance. Cassandra 4.0 features a standard, or well, not standard, but at least publicly available example with a stress profile for lightweight transactions. It's a profile for Cassandra stress. The name is SQL stress, LWT example, YAML, and so on. So we tried this profile using Cassandra stress from Cassandra 4.0. And this is important because this Cassandra stress tool is not shard-aware. And of course, it is best to use shard-aware drivers with lightweight transactions, so you get best performance with lightweight transactions also when you use a shard-aware driver. So I'm mentioning all of this so that you sort of can keep this in mind when looking at the next slides. And we also, no, I would like to go over the replication factor and so. And you can also see that the row size is fairly big here. And we tested the limits of lightweight transactions. So we tried to saturate the Scylla with queries. It was a very powerful loader that we used to generate the load. So next slide, please. So, and here I also compare, just to give you a perspective, everybody's asking, when are you guys going to publish Cassandra benchmarks? I prefer to avoid that kind of benchmarking. So I'd rather talk about the implementation differences, and then you can draw your conclusions yourself. Besides, as I mentioned, this is not shard-aware driver, so this is not the best that you can get from it, but it's also looking quite good. And if you have been using Cassandra, then you know that this is a very good performance that we are showing here. So just let's take a look at this slide. And we test actually up to 1,000 clients. The highest setting that the benchmark is testing is about 913 13 threads, independent Cassandra stress threads. And we reach peak performance at around 300 clients here, you can see. So I also present two versions here. The one you have already available today, 3.2 release, which was branched off like a couple of months ago. So it doesn't have the most important, like the newest optimizations that I'm going to talk about. And also 3.3 with the three important optimizations related to reducing the number of round trips, ensuring that the transaction is always executed on the right shard. And this particular build is without actually the next optimization or a fix that we did, that syncing the commit log on every write. So this is not syncing the commit log on every write. So you can see that the peak performance on 3.3 is around 30,000 transactions per second. These are quite heavy queries. As you can see, it's like the blocks that the Cassandra stress generates contain 4 kilobytes of like blog posts, and the title, like up to 300 bytes of title, up to 200 bytes of author name, and so on. So so this could even be seen as a fairly saturating the network benchmark. And we have been using the European data center from Amazon. It doesn't my feeling is it doesn't have as good latencies as the American data center, just closer to me. I'm in Moscow time. So, and let's look at the latencies actually. Next slide, please. So you can watch the performance or the saturation by watching the latencies. So the latencies are decent, and this is 99th percentile, decent while you have up to like 50 clients. So if you go back to the previous slide, yes. So in 50 clients, we are about like 15 to 20,000, right? Or yeah, 15, roughly 10 to 15,000 queries per second. So that's when the latencies are decent. When you double the load or triple the load, like in, let's take a look at 300 clients, your latencies is around 10 to 20 milliseconds. This is not something unusual. Let's take a look at the implementation and to understand what is actually going on so that the latencies are so high. Next slide, please. So if you're familiar with or just a fan of distributed protocols, as many people are nowadays are, then you probably know the major differences between leader-based and leaderless consensus protocols. Paxos was introduced in 1899 and popularized after this famous paper, Paxos Made Simple by Leslie Lamport, who is the original author. And it has two major rounds that involve all of the participants. So the first round is a proposed round when we elect the leader for the current sort of for the round itself. And it involves sending a query to all of the replicas from the coordinator, asking for the permission to do the update. The second round of Paxos is the accept round when the leader knows that he's going to be like the next, the only node that is working with this key for the next sort of quant step or whatever. Then the leader can send the new mutation to the replicas. And once the leader knows that the decision was made, that the majority of replicas accepted this new value, then he can inform the replicas, and this is like optional part, but it still needs to be done before the next round, that the decision was made, so that the replicas can safely store the new mutation in their durable database. So next slide, please. In addition to that, Cassandra has this check condition round, which fetches the old row or the checksum of the old row from replicas between propose and accept. So all in all, there are 4 round trips in Cassandra to perform the mutation. And the initial implementation that we benchmarked at 3.2 that we've just released followed that. And basically, you can see this explains why you have like in a data center where round trip time is in millisecond or 1 or 2 milliseconds, you have up to 20 milliseconds for the statement itself in a loaded case. And also you need to read the old record from SSD. So this also takes time. Next slide, please. So Scylla worked on optimizing the protocol since the first version. And I would like to talk about 3 important optimizations. One is, I sort of mentioned already, is ensuring that in most cases, there are only 3 round trips instead of 4. The second one is making lightweight transactions always durable. And the third one is reducing contention. Those of you who are familiar with Cassandra probably know that if you update the same key from many clients, then the performance can be actually quite good, quite bad, I'm sorry, down to 1 query per second and even lower. Next slide, please. So how do we actually reduce the rounds? We optimistically ask the participants which accept our leader role in the first round to send us the old value. This could be slower under contention, but in most cases, the leader, especially with shard-aware driver, when client prefers a certain replica for a certain token and sends a mutation against that token to that replica, the leader tends to stay the same. So we use that heuristics to reduce the check condition, to remove the check condition round. And if we fail at getting the mutation or at being elected as a leader, we fall back at the safe option, and this is the 4 rounds as the previous value of the version of the protocol, or we can do this as well if we need to repair the participants. The second, next slide, please. So the second change that we've made since 3.2, and hopefully it will be available in 3.3, is ensuring that lightweight transaction rights are always durable. Here we talk about transactions. So this is some sensitive data which would never want to lose. And you probably know that Scylla has 2 modes of maintaining the commit log. These modes are more or less the same as in Cassandra. So it's a batch mode and a periodic mode. A batch mode ensures that every write you do to the commit log is immediately flushed to disk. So the transaction or the change is not confirmed before it's written to disk. The periodic mode collects a lot of batches, a lot of mutations from a lot of writes, and flushes them as soon as, actually periodically, or as soon as they reach a certain size. So when you sort of run out of commit log buffer space. So we had an option whether or not to turn on the batch mode by default for everybody who wants to use lightweight transactions. This is kind of expensive. So it's like, if you want to use lightweight transactions, you have to pay for it, even though it might be like 2% or 5% of your load profile. So we introduced a combination which always works. Whenever there is a transactional write, we sync the commit log with all the pending writes so far, even in a periodic mode. So we made sure that lightweight transactions are always durable in all modes, and you don't need to tweak your commit log sync settings just to use lightweight transactions. Next slide, please. So the next thing we did is being more friendly to drivers that don't support shard awareness. So you probably already know that it is not nice when you have to introduce an extra hop just to write your mutation because you initially sent it to the shard which is not responsible for the token corresponding to the mutation. This is not nice for standard mutations, and this is like 3-fold or four times less nice for lightweight transactions, because lightweight transactions need to do like 4 round trips or 3 to 4 round trips and they involve like all of the replicas just for that. So in case a mutation arrives to the wrong shard, we first send it to the right shard and only then send it to the corresponding shards on replica nodes. And the corresponding shards are going to be the right shards as well, because this is the way communication between Scylla nodes works. So we avoid this hopping between shards just from the beginning. Next slide, please. So with that, I would like to talk a little bit about future. We keep working on Raft. We keep working on optimizing lightweight transactions and making them better. Like right now, we are looking at Jepson testing, at distributed testing, load testing. So making sure that the version you're gonna get as a stable version this year is really going to be stable, is really going to live up to your expectations. And besides, we also work on sort of a different direction, or not different, but complementary direction. So we would like to have all transactional tables, which are always transactional. And for that, we work on a number of changes, including a new replication strategy, a new partitioning scheme, and basically you can see on the slide. So this is going to be a lot of changes. So with that, I would like to hand back to Zaf and to talk about the roadmap and the future of LWT and Scylla.
Thanks, Kostya. So usually product managers are not a fan of presenting roadmaps, but since I'm expecting a question around that, I will go ahead and show our plan. You can put the disclaimer, it's just a plan. We're likely going to change it. So as mentioned, lightweight transaction already available as experimental feature in Scylla 3.2. You can go ahead, download Scylla 3.2, try lightweight transaction, and share your feedback. We are planning to productize lightweight transaction in this quarter, meaning by the end of March. It might be under the name Scylla 4.0 or 3.3 or 3.4, we're not sure yet, but most of the work that we're doing right now with lightweight transaction is stabilization and testing. And once the feature mature a bit in the open source community, we will backport it to Scylla Enterprise. And you will have the slides, you no need to copy, you will have the slide after this presentation, and you can go ahead and download the Scylla 3.2 with lightweight transaction as experimental feature. And by that, let me switch to the Q&A. Okay, the first question, and Kostya, I guess it's for you. How much impact on performance do lightweight transaction have compared to not using lightweight transaction?
So it doesn't have any impact if you don't use them to begin with, right? And if you just compare non-transactional write, we need to separate the reads and writes here. Okay, so for reads, it is maybe only twice as expensive because the only difference between a lightweight transactional read and just a standard read is that we need to make sure that nobody is updating this key while we are doing the read. So there is an extra round trip for that. For writes, it's more round trips, like 3 times in a good case, but there is also a hidden read. So the hidden read is actually the devil here. And then the cost of the hidden read depends on your whether it hits the cache or it hits the disk. So what's your data distribution? What's your scenario? How much you actually have to read, like whether you're always small or big. So having said that, I think it can be between 3 times and 100 times. So that's a lot by any definition.
Okay, thanks. Next question. Are multi-partition conditional batch supported? I think you mentioned that actually.
I mentioned that we perform the round on the partition key basis. By implication, that means that you cannot use, just like in Cassandra, you cannot use multiple partitions inside the same batch. So you can use, but it's not going to be a conditional batch. All right. So if you use conditions and you use multiple partition, you're going to get an exception.
Okay. And the next question from the same person. Can lightweight transaction be mixed with user write for the same data? Actually, I wanted to ask the same. So
yeah, so you need to know what you're doing. And in certain cases, for certain scenarios, it can, but there are cases in which it would return different results. Just to give you an example. So the accept round of lightweight transaction stores the mutation in a special system table called the system Paxos. So once the mutation is stored at the majority of the replicas, it is considered committed. It's like, it's not something we can, it's not arbitrary, it's a distributed state machine change. If the majority has stored the record, then the record is committed. It has to be committed and stored in the base table eventually. So, but there can be a failure between like accept phase and commit phase. And the record will fail to move from the Paxos table to the base table. So if you use reads with lightweight transactions and you use just quorum reads, you will not see this event, which means you might read somewhat stale data, but it's always going to be committed data. So in this sense, like it's okay. The data you're going to be reading is the committed data. So in this regard, it is safe, but it's not always the latest data. So they are not equivalent for that reason.
Okay, thanks. Next question. How good can Scylla lightweight transaction in handling a contention? For example, 100 client trying to access the same row, I guess, or field and update it in the same time.
Yeah, so this is actually an excellent question. So contention is a Achilles heel of Paxos because some even do not consider Paxos live because of this contention issue. And the way Scylla responds to contentious updates against the same key is the same as Cassandra generally. So, you know, if another coordinator wants to update this key while another update is in progress, the current update has to yield to the coordinator, so to the new coordinator. So this may lead to timeouts under load, and this may lead to actually significant performance degradation under load. Having said that, there are some important differences between Scylla and Cassandra that we have made already, and we hope to also work on reducing the problem in the future. So one difference I mentioned is like the bounce to shard optimization. Before proceeding with the update, we first forward it to the right shard. And there's a queue on that shard for all of the incoming lightweight transactional updates. So if you happen to hit the same coordinator with all of you from all of your clients, they're actually going to queue up. And the performance is not going to be significantly impacted. However, if you're not using shard-aware drivers or you are hitting different replicas with the same write from different clients, then so may happen that all of the participants starts trying to update the same key. It's still not as bad as in fully contended case, because it's going to be the number of participants is going to be as big as the number of your replicas that are responsible for this token. So it can be like 3 or 5 times as bad. Anyway, it's not a good thing in any case. So we are looking at other optimizations and other improvements that can solve this issue, but this is the state right now. So better, so from algorithmic point of view, better than Cassandra, but not as good as we would want it to be yet. And I would love to present the benchmarks about it. However, like as I mentioned, Cassandra Stress 4.0 doesn't have shard-aware driver, so it's not easy to do with the Cassandra Stress. And I would like to use a standard tool for benchmarking.
Okay, thanks. Next question, I guess I can try and answer it. So the question is alternator using lightweight transactions? So for those of you who are not familiar with alternator, it's another API that we are adding to the Scylla. It's an AWS DynamoDB compatible API based on REST and JSON. It's equivalent, if you can think about it, to CQL, which is compatible to Cassandra. We now have another API which is compatible to AWS DynamoDB. And if you're familiar with the API of DynamoDB, it does have conditional updates. And the natural thing for us, as we did, is to implement this API over lightweight transaction. And from that, you can conclude that the alternator is, as Lightweight Transaction itself, still in experimental mode. But if you are using Scylla 3.2, you can already try alternator as well. And we do hope, and we will make a GA in the next few months. Last question for today, for you, Kostya. Were newer protocol like ePaxos evaluate for Lightweight Transaction? Did you look at something like ePaxos before implementing?
Yes, so I could probably give another webinar on the differences and the hype in all of the Paxos family protocols. So we try to look at the optimizations that are not only efficient, but also are simple, because many of these optimizations that are theoretically feasible would be very difficult to implement and support. So the closest equivalent that we have been looking at is Paxos leases. So make sure that the leader stays the same for the next round if it was elected for the previous round, and somehow introduce some bias in the way we elect leaders for keys, like always select the primary replica for the leader. There is a sort of a general direction in Scylla towards RAFT. So we learned a lot in our initial attempts to implement RAFT. We learned that we would maintain a lot of RAFT state because there are a lot of groups, natural RAFT groups in Scylla because of the way data is partitioned. So this is why we are now looking at a different partitioning scheme for fully RAFT tables. So so these are the two directions that we can do. We can optimize the existing Paxos, or we can actually implement RAFT for tables that are designed for it and get the optimal performance.
Okay, thank you, Kostya, and we'll wrap up with that. Sorry, I see more questions, but we're out of time. So you have our contacts, and you are more than welcome to email us or jump to the Scylla Slack channel and ask more questions, and we'll do our best to answer. So thank you, Kostya. Have a good night. For myself, it's good night as well. And I guess for most of the people here, it's a good day or good noon and such. So thank you very much. Bye.
Good time of the day on your part of the galaxy, yes.
Bye, guys.